Welcome to the next video in the group theory series. In this video, we introduce matrix groups. To begin with, we focus on the operation of addition. If we are to add two matrices, so for example, this matrix 1, 2, 3, 4, and the matrix 5, 6, 7, 8, then we perform the addition coordinate-wise and get 1 plus 5 is 6, 2 plus, or sorry, 1 plus 5, yes, 1 plus 5 is 6, 2 plus 6 is 8, 3 and 7, 10, 4 and 8, 12. So, if we are to perform, or if we are to add two matrices, then they must have precisely the same dimension. Addition is performed coordinate-wise, so if the dimensions mismatch, then we will be unable to pair some coordinate with of one matrix with the other, and the sum will be undefined. We can define this operation using any number set for the coordinates. So I'll use a double struct x to represent any choice of number set from the sets, right, either the integers, rationals, reals, or complex. To denote the set of m by n matrices with these coordinates for any positive natural numbers m and n, we write that set with a superscript m cross n. If we want to argue that the operation is closed, we need to take any matrices A and B in this set of matrices and show that the sum is also in the set of matrices. There is a way in which this just inherits from the closure of the underlying number set under addition. Of course, that's true no matter which number set we pick. To help with some notation, let's agree that for any matrix, we write that matrix in parens with subscript I comma j to mean the element of A at row I column j, with I going between 1 and m, of course an integer, and j between 1 and n, again an integer. To argue for closure, we know that A plus B will, by definition, be an m by n grid, and by definition of coordinate-wise addition, then the ij coordinate of the sum A plus B is the ij coordinate of A plus the ij coordinate of B. But those, right, the ij coordinate of A and the ij coordinate of B are, by our earlier assumption, elements of this number set, double struct X, and X is closed under addition, so their sum is in double struct X. Therefore, A plus B, right? Since that is true at every coordinate, then that is exactly the condition that we need to ensure in order to know that A plus B is an m by n matrix with coordinates in X. We can repeat a similar inheritance argument for associativity as I have in the page to the left. The confirmation that there is an identity element, the matrix of all zeros, which we write as m to the m, or sorry, 0 to the m cross n, and that it has all inverses is straightforward, so I skip it. In some sense, the whole point of matrices is to multiply them. So we should talk about that. we will again require matrices of the same dimension, but moreover, we require square matrices. So A in x to the n cross n. As you can see to the left, without this requirement, even if AB is defined, we wouldn't have BA defined, and in group theory, we require all products to be defined. Just as we saw with number groups, matrices x to the m cross n do not form a group under multiplication because so many elements fail to have inverses. A good non-zero example, even with coordinates in the rationals, is the matrix 1, 0, 0, 0. However, we can get a group by restricting to those matrices with an inverse. This sort of brute force turns it into a group. This is especially important when X is among the number sets Q, R, or C for reasons we'll have to discuss only when, in a future series, we talk about rings and fields. Note from linear algebra that with X in one of these number sets, a matrix in X to the n cross n has an inverse if and only if its determinant is non-zero. And we may write the determinant as det, or we may write it with these absolute value bars surrounding the matrix. Therefore, we define the nth linear group, general linear group, as GL sub n of X. And that just refers to all n by n matrices with coordinates in X such that their determinant is non-zero, which is precisely the invertible matrices. Note that closure becomes an important thing to check since it is not immediately obvious that if A has non-zero determinant and B has non-zero determinant, then their product must also have non-zero determinant. That's the closure property that we would need. But with the help of a useful theorem, we in fact have that that the determinant of the product is the product of the determinants. Now, if we know that A has non-zero determinant and B has non-zero determinant, then this product is not zero, and that demonstrates the closure property. Of course, the matrix, the identity matrix, here I'm writing it in GL sub 2 just for convenience. But in general, for GL sub n, the identity matrix for an n by n matrix acts as the identity matrix in this group, and it has determinant equal to 1 and therefore not 0, so it is in the set, right? So, so this group or the set has an identity element. Before ending, we should point out one more group, which is a subset of GLN, right? The nth general linear group with coordinates in X. This is the nth special linear group, SLN of X. And it is specifically all of those matrices, n by n matrices with coordinates in X, which have determinant equal to 1, a more specific and stronger condition than just non-zero. So for the case when n is equal to 2, and especially when the number set is the real numbers, this is interesting for us because these matrices represent all transformations of R squared, the plane, which leave lengths and angles fixed. In this case, it therefore can be proven to contain precisely the rotation and every rotation and reflection about the origin. An interesting tie-in with D sub 2n. Note how closure follows from if two matrices have determinant equal to 1, then by that very similar argument to the one given earlier, The determinant of the product is the product of the determinant is equal to 1 times 1 is 1. And I forgot to expand all of this stuff in the typed notes, so you can see it here.